Good morning, everyone. Today we are going to continue our talk about the phase diagrams. You can see this is the third time for us to talk about phase diagrams. We will talk about this topic using other uh, class sessions as well. You can see how important it is. And today's objective is very simple, and one objective and learn eutectic systems. So this is very important. Eutectic systems. Uh, in the previous class, actually two class sessions, we talked about the binary isomorphous system. And binary isomorphous system, it means that we have two components. And for our case, it is a copper. And we have this copper and nickel to get the brass. The alloy is a brass. So binary, this is a binary. Isomorphous means that so this is a nickel can be dissolved in this is a copper from 0% to 100%, and that means these two guys are soluble to each other from 0% to 100%. And we also have learned for this binary isomorphous system, we have three. This is the phase fields, and here is the liquid, and here is alpha, the solid, and in between these two curves, this curve is called a liquidus line, and so this curve is called a solidus line. And between these two curves, and we call, so this is the coexistence of L and this alpha. That means we have both L phase and also alpha phase. This is what we have learned. Any questions regarding this slide? No question. We talk about the binary eutectic system. So this is more uh, complicated than the previous one. So you can see, so this is a copper here, and so this is a silver. This is a copper and silver. This is we know that for the copper with the nickel, and they are binary isomorphous phase diagram. But here, copper and this is silver, and they have a different phase diagram. We call binary eutectic system, binary phase diagram. So here is copper from 0, from this 100, this is silver. And so here is, this is the ordinate is the temperature degree C, and we can see, and so here is liquidus. This liquidus separates this part into this one for solid liquid, and so this is solid. So here is alpha. So, okay, this is alpha phase alpha. So here is a solidus one. So here is a solidus one, and this is a solidus, and this is solvus. This is solvus. I'm sorry. This is solvus, and solvus is used to separate and two different solids here. And so this is a B point here, and within this area, and we have two the phases. One is alpha. One is alpha is a solid. L is the liquid. And so for this is the in this area. And here at point E here, okay, at point E, so this is the liquid above E, and below E it is the two solids, two solid phases, and they are the solid solution. And here in this part, so this part, we have on this extreme, okay, this extreme, we have beta, this beta here. For here, in between this liquid and this is the solid beta, we have two phases. One is beta and one is L, this liquid. So we can see, so this phase diagram is much more complicated, right? So than the previously talked, this is a binary isomorphous the diagram, and we can see how many solid phases we have. We have alpha, and we have beta, and so these are two different phase, solid phases. And we have L here. How many lines we have? Liquidus line. This is liquidus line. So this is also liquidus line. This is solidus line, and this is also solidus line. And this line is called solvus. And solvus curve is used to separate different the solid phases. And any question regarding this phase diagram? This is a very, very important one. Okay, so here is for each of these points, we have associated this composition and also temperature. Questions so far? Okay, it seems that you understand all these things, right? So then we are going to use this phase diagram and to calculate the weight percentage, or to calculate the composition of different phases using the rules we just talked about in our previous class session. So binary eutectic system, what does it mean? Right? It means that binary means that two components. For this case, we have copper and silver, these two different elements. And eutectic has a special composition with a minimum melting temperature T. Okay? Has a special composition with a minimum melting temperature T. We can know that at this temperature with the lowest one, we have, if the composition equals CE is eutectic, and the composition, we call this one eutectic composition. At this point, we have the lowest melting temperature. Did that make sense? Okay, and so if we write this is a chemical reaction equation, we can, for this point, we have L, and this is CE eutectic composition. If we cool this liquid, we will have two different solid phases, and alpha, beta, and please note, so this alpha, C alpha E, and beta is C beta E. Any questions so far? See, this is C alpha for this is a eutectic composition. This is beta for eutectic composition. Three single phase regions, and liquid, alpha, beta. This is what I just talked about in our previous slide. A limited solubility, right? So limited solubility. You can see alpha, right? This is alpha. Mostly for this alpha, mostly copper, and for this beta, mostly it contains the silver. And TE, right? You can TE for the temperature of eutectic temperature or eutectic temperature, no liquid below this TE. That means, so this one, if you go below, this is eutectic temperature, and you will get the two solid phases immediately from this is a liquid phase L. This is very beautiful, the property we can use. Any questions regarding this slide? And also, as I said, CE is composition at the temperature and TE. So this is a special point, and this point is a special point. It's called eutectic point. And we can, for this one, we can eutectic temperature, which is the lowest melting temperature at this eutectic composition. Questions so far? No question? And we move on to the next slide. And next example, this example is an PbSN eutectic system. And previously we talked about copper and silver, and here is the lead and tin eutectic system. So you can see, right, we also have alpha, beta here, this L plus alpha, L plus beta. So here we have two solid phases, alpha and beta. For this point is eutectic point, and for this eutectic point, and we know this is eutectic composition and also eutectic temperature. So you should know how to read the phase diagram. And for example, here, okay, this is statement for 40 weight percent, and this is tin, and 60% of this is the lead alloy at 150, and determine the phase present, right? And so if we know the composition and also the corresponding temperature and the temperature, we can get a point in the phase diagram. And so answer alpha and beta. For this point, what kind of phases are present? And we know alpha and beta. Second one, the phase composition. Right, the phase composition. This is a phase composition, and we draw a vertical line. And can you tell me what do we call this vertical line when we interpret this phase diagram? It's called tie line. Okay, so we call tie line, and we call tie line. Right, we call tie line. This tie line, this horizontal line, intersects this Sauer's curve at this point. And then we draw a vertical line. We know this is 11%. And so this is for alpha. So similarly, we extend this horizontal line and which intersects so this Sauer's curve. And then we get this point. Then we draw a vertical line passing this point, and then we know so this is the composition of beta. As a result, and the composition of alpha equals 11 weight percent of this tin, and beta equals 99% of the tin. Any questions so far? No question? It looks like you are very, very engaged in this topic, right? Okay. And the relative amount of each phase, and so this is, we use Lever's rule. We still use this timeline. Okay, we have R and S, and we know this the length of these two arms, and about this is C0 here, and we know this W alpha and W beta, and last time we know and how to calculate this weight percentage. And for W alpha, okay, for this W alpha, and we use the length of the arm that is opposite to alpha. That means for beta, this one is the numerator here, and we just plug in, we can get, so this gets the weight percent. And similarly for this beta phase, and we also use this equation, but then this time the numerator is the length of the arm that is to the left of this given point C0, and then we plug in this is the compositions, and then we can calculate W alpha equals 0.33. Any questions so far? This is how we calculate, how we interpret this is phase diagram. For this lead and tin eutectic system. Questions so far? No question? And then we take a look at another point. Right? So another point is on 40%, 60% composition is the same, however, and different temperature. And now this time, so this point is located in, so this area, which includes both the liquid alpha phase and also the alpha phase. The present phases present, we have two phases, just as I said, liquid phase and solid alpha phase. And the phase composition, and phase composition, just draw a tie line. This tie line intersects, so this is a solidus curve and this liquidus curve at these two given points respectively. And so you can just calculate C alpha equals this one, and this is C alpha here, and this is Cl, this is liquidus, and Cl equals 46% of this tin. C alpha equals 70%. The relative amount of each phase, we still use Lever's rule, and draw a line here, and get this is the two arm lengths R and S, and then we calculate this W alpha and WL, and based on this equation. Remember, so for these two guys, they have the same denominator, but the numerator are different. The two numerators are different, and be very, very careful. Okay, so this is a Lever rule. This is a Lever rule. And then we talk about microstructure development in the eutectic system. For alloys for which this is the composition is less than 2% of this weight percent of the tin here, right? So results at room temperature, if you go down all the way down from 400 more than about 400 to all the way down to the room temperature, and you will have what? Okay, so you have this liquid and go to get alpha. So this is a liquid, and then here at this point, and this is some dark dots. This is dark circle. We should not call circle. This is irregular. This is dots. We call these dots. Appear. These dots is alpha. Right? These dots are alpha. This green portion is still the liquid. And then when we go all the way down into this alpha, the field, we will have this is alpha. We will have polycrystalline. This is solid, the phase alpha. You can. This is the green boundaries. Second one, and if we have a different composition, which is a little bit far away from this is y-axis, and for example, for tin, when the tin is less than 80.3%, but greater than 2%, and from here and to 82%, from here, right, from here and to here, what will happen? And we just without loss of generality, we just draw this line to see what will happen. The result is at temperature, this is L, okay, in alpha plus beta range, and we will have here we have alpha and beta grains and small beta phase particles. So here and so this is all this liquid phase, and here and so with the solidification started, and we will have solid these particles alpha as shown in this circle. If we go here, go into this and shaded area, and we will have polycrystalline this alpha the phase. And then if we go further down, and when we pass this point and enter this area, alpha plus beta area, and we will have this. So this is alpha, and this beta is the particles, the tiny particles, and the tiny particles are embedded and in this is these grains, alpha grains. Then we talk about microstructure development in eutectic system. And for alloys of composition, see when the composition equals this eutectic composition, what will happen? Results eutectic microstructure, and we have lamellar structure, alternating layers. We call lamella of alpha and beta phases. You can see very, very beautiful. For this point, for this is composition. At this point, which is above the eutectic temperature, we will have this liquid phase. And when we go down a little bit, we will have, so this is alpha 80.3% weight of tin, and draw here, and beta, okay, beta, alpha, beta. So these are alternating layers. So this is alpha 18.3 weight percent of tin, and beta is 97.8%. The tin is very, very high. And draw this line and to get this composition of alpha and the composition of beta. And so this is a micrograph of micrograph of lead and tin eutectic microstructure. So this is very, very beautiful. Do you guys agree? And just like the tiger, the skin is very, very beautiful. And lamellar eutectic structure. Lamellar eutectic structure. So here, so this we know beta has a very, very high, the very, very high this tin this content, and the alpha has very, very high. This is lead. So you can see this is a liquid. Okay, so eutectic growth direction. This is a liquid, so this is solid. When it moves, so this is a beta. Okay, so this for this beta phase, so these lead atoms will go away from beta from this area and go to the neighboring area, as shown in orange. And same thing for the orange area. So all this which contains alpha solid phase, the tin will go away from this area and go to the blue area. As the time goes here, and so this is a beta, so go this way, alpha go this way, so on and so forth. And we will know that beta has a very, very high percentage of this tin. Alpha has a very, very high percentage of lead. And this is a micrograph, and this is very, very like this. This looks like the tiger's the beautiful skin, beautiful fur. Right? And questions so far? If no question, and then we for alloys, we just give you example. One for 80% weight. So this is for which is higher than 80.3%, but lower than 61%. And so we want to calculate alpha phase particles, and we get alpha phase particles, and we get this eutectic macro constituent. So here at this point, L alpha, when we just go down a little bit lower than this liquidus line, liquidus curve. So here just above this, so this horizontal line, and we just draw this tie line horizontally, get this R and S. For here we will still have liquid, and we still will have bigger particle, alpha particles. And if we go a little bit further down, lower than this horizontal line, right? So we will have, and so these kind of things. So this is primary, this is alpha. So these are primary alpha. So these are particles. This is primary alpha. And however, for this liquid here, okay, and this liquid will come have, this is the alpha and beta. So these alpha beta alternating layers. These alternating layers, for this one still have alpha, is called eutectic alpha, but here will be eutectic beta. And please note that primary alpha and eutectic alpha, they are different. Do you have sense? Okay, and we also say just above this eutectic temperature for this one, we can calculate a composition of alpha, composition of L using this timeline, and also using the level rule and to calculate the weight percentage of alpha and L. The same thing, similar thing for this is the point just below this is eutectic temperature, and we can get this C alpha, C beta using the this timeline and get this weight percentage of alpha and weight percentage of beta. So this is the very, very beautiful microstructures. So this is one of the reasons that I like material science class very, very much. Then we talk about hypereutectic and hypoeutectic and hypereutectic. All right, so we still use this is the lead and tin system as example. So this is the eutectic, right? This eutectic. So for this is a composition range from this point and this point, and we call hypoeutectic. This is hypoeutectic. And from this is the eutectic composition and to this point, and we call hypereutectic. And be very, very careful when we take a quiz or exam. I might ask you guys to use your own words and to explain what hypoeutectic is and what hypereutectic is using your own words. So here, for eutectic, we have this beautiful lamella. And for this is a hypo, in addition to this is a beautiful lamella, and we will have primary alpha here. Okay, so this is primary alpha. And similarly, for the hypereutectic, and in addition to this is a lamella, beautiful lamella, and we have primary beta particles embedded, and in this is the micrograph. So this you can see is very, very beautiful. Right? So this is material science.